So let's formalize some of the things that we just talked about in terms of a couple of definitions. Maybe I shouldn't say anything on this. So I'm going to define a critical point. We say that a point AB is a critical point if one of the two criteria holds. So either we have both the partial derivative with respect to x is equal to 0 and the partial derivative with respect to y is equal to 0. That's one way that a point could be a critical point. Or a second way that a point could be a critical point could be if the partial derivative with respect to x at that point AB or the partial derivative with respect to y at that point AB do not exist. So notice that the definition of critical point is a little more complicated for multivariable functions than it was for single variable functions. We have two different ways that you can have a point be a critical point. The traditional way, is that both the partial derivatives are equal to 0. That's one way that you could have a critical point. Another way we could have a critical point would be if the partial derivatives are undefined or don't exist at that point. And we'll see some examples of some of these later. Why are critical points interesting? We have this theorem that tells us about critical points. Any point that's either a max or a min must be a critical point. So it means that if I find my critical points, I can evaluate whether those points are maximum or minimum values. That's going to give me my max and my min values. Notice, this is my little note, that it's possible to have critical points that aren't maxes or mins. Just like we saw in the graph previously, at that point B, we had a critical point where the derivative was equal to 0, but it wasn't a max or a min. It was sort of a dud right in the middle. The same thing can happen in multivariable functions as well. So let's go ahead and take a look at an example. So let's look at an example. Let's say that we're given a function f of xy is equal to x minus 2 quantity squared plus y plus 1 quantity squared. And I want to evaluate what are the critical points of this graph. As we saw before, the only way to find critical points would be by first finding partial derivatives. So my first step in finding critical points, maybe I should write that, find critical points. I'm going to take my partial derivative with respect to x. And I see that in this case, I'm going to use chain rule, and I get 2 times x minus 2 times the derivative of the inside stuff, which is nothing. I can simplify this, and I get 2x minus 4. Notice that this is a continuous function. It's not going to have any gaps or holes, so I don't have to worry about criteria 2. I know that my partial derivative with respect to x is always going to exist. So I'm thinking about my first criteria. When is my partial derivative with respect to x equal to 0? So if I set this equal to 0, I add 4, and I find out that that means that x must be equal to 2. Similarly, I'm going to take my partial derivative with respect to y of this function, which is going to be 2 times y plus 1, which is equal to 2y plus 2. And this, again, is a continuous function. I know I'm not going to have any problems with this partial derivative not existing. So I'm going to set it equal to 0, and I find that y is equal to -1. These are the only possible x and y values that I get out. So I found that I have a critical point at the point 2, -1. Let's evaluate this graphically to find out what it means in terms of 2, -1 as a max value, a min value, or neither. Looking at this function, we see that it has the basic setup of our paraboloid. If I wanted to, I could do a bunch of horizontal and vertical traces, or I could just think to myself, I know that my x's have been shifted forward 2 units, and my y's have been pulled back 1 unit. And it means that I have this paraboloid function that has the base of the paraboloid shifted over to this point 2, -1. And I could use three-dimensional graphing software to graph this as well if I wanted. But looking graphically, I can see that the point 2, -1 is going to be a minimum value. Next, let's consider another example. Let's think about the function g of xy that's given by the square root of x squared plus y squared, and evaluate the critical points for this function. So again, I'm going to do the same steps that I did before. I'm going to take my partial derivative of g with respect to x. I'm going to need to use chain rule in this case. And in order to use the polynomial rule, sometimes it's nice for me to think of this square root as being raised to the 1/2 power, because then it's easier for me to think about the polynomial rule when taking the chain rule. So the derivative with respect to x of this function is going to be the derivative of the outside of the function times the derivative of the inside. Treating y as a constant, I get 2x. Oh, sorry, derivative of the outside, it's going to need to be raised to the negative 1/2 power. If I can simplify some of this, the 1/2 times 2 cancel one another, and I end up with x divided by the square root of x squared plus y squared. So notice a couple of things. There are two things that we need to check in order for something to be a critical point. One way that this could be a critical point would be if both this partial and the partial with respect to y were equal to 0. So I can go ahead and solve and say, when is this equal to 0? And I see that my partial derivative with respect to x is equal to 0 when, in this case, the numerator is equal to 0, which is when x is equal to 0. I also see that right away the point 0, 0 is going to be a point that is undefined, that I have 0 over 0, and so that's something that's bad. And by bad I mean my partial derivative with respect to x would be undefined when both x and y are equal to 0. So I know by the second criteria right away that the point 0, 0 is a critical point. And it's a critical point not because the partials are equal to 0, but because it's not defined at 0. But I might be able to find some more critical points. So let's go ahead and solve. My partial with respect to y in this case is going to be 1/2 x squared plus y squared all raised to the negative 1/2 times 2y, which simplifies to be y divided by the square root of x squared plus y squared. And we get the same information out. We still see that 0, 0 is a critical point because my partial with respect to y is not defined at that point. Also, I see that my g of y is equal to 0 when y is equal to 0, but if both x and y is equal to 0, then neither of these are defined. So this is an example where our critical point is falling into category 2, the one where the partials aren't defined. Let's analyze briefly, geometrically, what's going on in this case. So in this case, I'm thinking about this function. If I wanted to do some horizontal and vertical traces, if I set, maybe I'll do my horizontal trace where z equals 0 is a boring one, so I'm going to set z equal to 4. And what do I get out? It means that 4 is going to be equal to the square root of x squared plus y squared. If I square both sides, it means that 16 is equal to x squared plus y squared. And in general, all of my horizontal traces are going to be circles. So I know that I do have some circles. It looks like it could be something similar to a paraboloid. It turns out it's not. If I look at my vertical trace, let's set y equal to 0 for one of the vertical traces. I see that z is equal to the square root of x squared. If I square both sides, I'm adding in an extra element, but I see that z, well, maybe I don't want to do that. Maybe I'll just say that if z is equal to the square root of x squared, we know that by the domain of x squared, which isn't a one-to-one function, I could have both positive and negative values. Or I could square both sides and then square root both sides again, and I see that z is equal to plus or minus x. Either way, it means that this is actually just a straight line. And so my image is going to have circles in the xy plane and straight lines in the yz plane, meaning that this function looks like a cone. It's one that you explored on your homework for 4.1. And we see that 0, 0 is a critical point. It turns out that it's actually a min, just by graphical analysis. And it makes sense that my partial derivatives are not defined because they're pointy right there. This is a cusp point. And there are an infinite number of tangent planes that I could set here. So it makes sense that we have this case where my partial derivatives are not defined correspond with this sharp pointy place on the cone. And so it is still a minimum value. It's just one that fell into category 2. Gosh, that was a... So finally, we're going to look at one more example, and I'm going to move pretty quickly through this example, that I want to find the critical points of the function h of xy is equal to 3x squared minus y squared. We're going to do the same steps that we did before. I'm going to take my partial derivative with respect to x, and I get 6x. And I want to know, when is this equal to 0? This is going to be equal to 0 when x equals 0. Similarly, when I take my partial derivative of h with respect to y, I end up with negative 2y, and I set that equal to 0, and that's equal to 0 when y equals 0 as well. So it means that 0, 0 is a critical point falling into the first category type of critical point. And I want to know whether or not this is a max or a min. In order to do that, I'm going to do a quick graphical analysis by looking at the horizontal... No, I'm actually just going to look at the vertical traces in this case. We see that when y is equal to 0, we end up with a parabola that's upward pointing in the x-plane, something that looks like this. And this is just in the xz plane. We see that when x is equal to 0, we have a downward sloping parabola. And if I fill in the pieces of this function, we recognize the fact that this is our hyperbolic paraboloid. And I have a parabola that's upward facing in the x direction. It's going to go up and over like that. And this back sheet is going to go up and over like that. So maybe that's a bad drawing, but you get the idea that it's this paraboloid sheet that's been stretched in a U downwards. So looking at this point 0, 0, we see that it's not going to be a local max. It's the highest along this parabola, but it's actually the lowest point along this parabola. And the name for this type of point is a saddle point. This is a critical point that's neither a max nor a min. And there are many different saddle points that you'll find investigating in your problem set.